Hello. So, we've seen previously, right, that we know it's sort of possible to reverse the derivative process to a point. So it's sort of worth taking a moment here to establish those rules, at least for the core functions, right, the parent functions that we're going to be using. So basically our goal here then is to record those relationships, right? The idea that, if we want to go backward for each of our core functions, what do we need to do? What do we get if we're trying to go backward? So before we do that, it's worth, again, reminding ourselves what those sort of going forward rules were, right? If we want to go and take the derivative, we want to know those rules so that we can try to go backwards. So our first one, right, this derivative of the polynomial rule, right, the derivative of the monomial, except it's sort of a little more than that, right, because the n can be any real number, right? So this could be square roots, cube roots, pi, whatever. It's all the same formula. And we have the, classic, we bring down the n, subtract 1 when we take the derivative, right? For a to the x, right, our exponential version, we have that natural log of a times a to the x. So we get that natural log of a coming out, but otherwise it's the same. And remember that we have that sort of special case. It follows the same rule, but at the special case where a is e. So when it's that irrational number e, the natural log of e is 1, and it's just itself, right? It's the do-nothing version function. And similarly for log, right, we have the rule for base b log. So any base b that is a strictly positive number. And we still have this 1 over x natural log of b, but when that b is, again, that irrational constant e, the natural log of e is 1, so we get just 1 over x. So again, it's the same formula in both cases, but when the base is e, we get this sort of especially nice result, right? So the goal then is to reverse this process. So to reverse the process, we quote-unquote simply, which, looking ahead, sometimes it's that simple. Most of the time it's not quite that simple. So we simply need to go backward with the equality. So the idea is that, we have the derivative rules here that are going forward. So our goal is to sort of go backward with this thing. We're going to go through each of these sort of one at a time. So polynomial rule, again, we sort of call it the polynomial rule, but it works for any kind of power, importantly including fractional powers, which is how you get the radicals and stuff. So our goal is to find a function f of x. By convention, we use capital F for this kind of thing, where when we take the derivative of that function, we get this nice x to the n, right? So we're looking for some function whose derivative is just x to the n. That's the goal. So we know, because of the way the derivative process works, right, that when we take a derivative of something that looks like some kind of x to the n thing, it subtracts 1 from the power. So we know we're going to need to boost that power by 1 so that when we subtract 1, we go back to what we wanted, right? So this is the idea. We're trying to reverse engineer it, right? So we can just start with that idea. So we'd start with f of x being x to the n plus 1. Now, we don't necessarily expect this to be the right answer, but the idea is that we sort of start with something that we think is close, see what happens, and then see if we need to tweak it to get the right answer, okay? So we have now a function, f of x. Now we want to test that, right? The f prime of x, we sort of hope, although we don't really expect at this point, that it'll be x to the n. So we take the derivative. So taking the derivative, we take that, right, beginning power, put it down in front, subtract 1, and we get this sort of n plus 1 times x to the n. So we have almost what we want, but not quite, right? We have that annoying n plus 1 in front. But the good news is that n plus 1, despite having a letter, right, n is some arbitrary constant, meaning it's some value, some number. In practice, when you're doing this, you'd be like, I need to find a function whose derivative is x to the 5th, right? Like you'd have a number there. So importantly, that n plus 1 is a constant, and constants go in and out of derivatives. So if we were to divide by that constant and then take a derivative, it wouldn't affect the derivative process. I wouldn't need things like a product rule because it's a constant, right? So this leads us to what our actual function is going to be, which is this same idea, right? The same x to the n plus 1, but now we're going to divide by that n plus 1 in anticipation of the fact that when we take the derivative, we're going to be multiplying by n plus 1, so they'll cancel out, right? This is the idea. And again, it's the same process. We have an idea of what we think is the right thing, so let's test it. We're going to take the derivative and see if we get x to the n. And sure enough, we will, right? So we take the derivative of this thing, and again, we remember, right, that 1 over n plus 1, whatever number that is, it's a constant, so it's not affected by the derivative. I can basically just ignore that 1 over n plus 1. So I get this n plus 1 on the top coming out front, and then subtract 1. When I subtract 1, I get x to the n, and this n plus 1 and the top and bottom, those both cancel, right? So I get exactly what I want. Okay, so I found one that works, right? Now, it is very easy to fall into the trap of thinking like this is the answer, but again, never quite as simple or as easy as we'd like. Unfortunately, this isn't the answer, it's an answer. And I realize this is not a thing that you're used to running into when you're talking about a math class, right? Like usually there is the right answer, not a right answer. Although in the real world, it's actually not uncommon to have a right answer as opposed to the right answer, but this is a whole different conversation. But what am I babbling about? What am I going on about? Well, remember that if we take the derivative of a constant, we get 0. But that means that if I sort of go back up and I look at my original f of x, that the piece that was just the 1 over n plus 1 times x to the n plus 1, right? Just this part before I took the derivative, I could add something to that. Plus 7, plus 13, plus pi, minus 6. Any of those things, if I took a derivative of them, they'd all be 0, so they do nothing after the derivative, and I'd get back to this x plus n every time. So adding any kind of constant would still be a right answer, okay? So we sort of capture all this information and sort of put it into one thing. We encapsulate it all into a plus c term. So this term is to denote the fact that we can have any constant. And again, this plus c is another one of those arbitrary constants. So if I have some function like f of x equals x to the n, then I can say, okay, well, I want some function f such that when I take the derivative, f prime of x gives me that original function, f of x. I know that that is this, right, this 1 over n plus 1 times x to the n plus 1, but it could be that plus any constant. So the actual formula then is going to be this f of x is that same, right, the 1 over n plus 1 times x to the n plus 1 plus c, right? And this plus c is really important because this plus c is actually capturing some important information. And when I say that, I don't mean like math is, important and we want to make sure that we get all the possible right answers. It turns out this plus c actually is there for a real life, real world reason. It actually represents real world information explicitly. And in fact, this plus c thing is so important that we're going to have a whole other thing on it. So I'm not going to dive into it too much more here. Just know that it turns out that this thing isn't just important for the sake of being thorough in a math class. It turns out that this thing is incredibly important whenever you're going to use this stuff in the real world in any context. Okay? So all of this stuff aside, right, the plus c thing is something that's going to come up a bunch, which is why we've sort of taken a second to really dive in on the polynomial rule, but it's going to come up with all the other ones because it's inherently the same problem. But now we have one for our polynomial, right? Again, this works for any sort of including fractional powers. So this would be also true for, the radical versions and things like that. So we have a version here. Again, almost. I realize you're probably getting sick of these little asterisks that are showing up. But if you're looking at this, there should be one possibility that's sort of pinging in your brain as a danger, right? So take a second to look at the formula. And as a hint, I'm claiming this works for any n. But there should be a particular n that really should be a danger here. So in particular, what happens right? Looking at the formula, what happens when n is -1? So just to think about it, right? We want n minus 1, go back for a second here. What would happen? The answer is sort of bad things would happen, right? So what about n equals -1? Well, if we tried to do that, our whole formula falls apart, right? Because we have that 1 over n plus 1 in the beginning. So if n is -1, we now have a 1 over 0. That's all kinds of bad, right? And on top of that, our power becomes 0. So it's not really, I mean, it is a polynomial, technically, but it sort of isn't what we would expect as a polynomial, right? So this is sort of a good observation, but step back a second and ask, okay, well, let's look at what the n equals -1 actually represents. What's it actually mean, right? So when n equals -1, what we're really asking is what function has as a derivative x to the -1. That x to the -1 is sort of more clearly written as 1 over x. And if you remember from the beginning, our rules of derivatives, this is actually sort of surprisingly a whole other thing, right? This is sort of a one-off case where the thing that has as a derivative 1 over x was natural log of x. Now, there's a little bit of, again, an asterisk here. So we have the plus c, but that'll show up all the time as we go forward. So that hopefully isn't too surprising. But what might be surprising is this crazy absolute value thing that's showing up here. And the reason why is because 1 over x has as a domain anything but 0, right? So I could plug in 5 pi 27, but I could also plug in -3, -2, -pi, whatever. But if I tried to claim, right, that my antiderivative, my sort of reversal of that process, this 1 over x, isn't just natural log of x, well, this thing is defined at -3, but natural log is not defined at -3. And it sort of turns out, again, with a little bit of magic happening here, although you can maybe convince yourself by just looking at a graph, but it turns out that if you use absolute value, analytically this makes sense because it forces it to be positive, and now we're happy, right? Because the 1 over x is not defined at 0. Natural log of absolute value of 0 would be a problem, but this isn't defined at 0 either, so we sort of avoid 0 sort of naturally even from the beginning. But all the other values, -2 becomes +2, natural log of 2 is nicely defined. Turns out this is exactly what we want. So that absolute value really is important when we're talking about sort of the natural domain of 1 over x, the fact that we could plug in negative values to 1 over x. A lot of the time, again, it sort of turns out in practice that when you have a situation where you're trying to reverse the process here and get the antiderivative for 1 over x, that you really only want the positive side. Sort of in practice, it is usually the case, which is why in practice, a lot of the times these absolute values get dropped, not because they aren't actually there, like not because they're not important, but because we already know that the input has to be positive for some other reason, right? Something inherent to the real world situation that's happening. So unless you have that information, right, unless this is a word problem where you know that x has to be positive, these absolute values end up being absolutely pivotal. So you got to make sure that you keep those, okay? Okay, so now we have a rule for that x to the n for any n. That -1 is this weird one-off, but all the other ones work. What about the exponential? Okay, so the good news here is that the exponential's much more straightforward than the polynomial ended up being, right? Which is a little weird because polynomials are supposed to be sort of the nicest functions, but there are all these little asterisks and footnotes that came up. So again, we start from the same sort of starting point. We want a function f of x such that when we take the derivative, we get this a to the x for some non-negative or positive a. So remembering, right, that the derivative, if we just look at the derivative of a to the x, we get itself plus that extra term, that natural log of a that sort of gets kicked out. But that thing's a constant, right? So just like we did with the polynomial, the core piece we know, right, is just going to stay the same. It's going to be a to the x. So we can start out with that as our sort of guess for f of x, right? We say, okay, I know it's not going to be quite right because there's going to be some weird constant kicking out, but the bulk, right, the function part, the parent function maybe is a way of thinking about it. That part's going to stay the same, so I'm going to start with that, see what happens, and then go back and adjust. So f of x, my initial guess is a to the x. I take a derivative. Unsurprisingly, I get natural log of a times a to the x. But again, I get this same, right, this natural log of a is still a constant. So we can do the same thing we did before, go back and adjust that f of x by dividing by that constant because the constant doesn't affect the derivative process. Also note, we still need that plus c, right? So we use the plus c, we're going to divide by that natural log of a so that it cancels out. We get our nice f of x formula is just 1 over natural log of a times a to the x plus c, so that when we take the derivative, we will indeed get back to where we want. So trying it, right? So again, we posited our idea, we try it, so now we multiply, right? Again, this 1 over natural log of a doesn't do anything because it's a constant, so it sort of just ignores the derivative process. This natural log of a gets kicked out when we take the derivative of a to the x, but these two things cancel. The derivative of the plus c is a constant, it's just 0, so I do indeed get back to a to the x. So this gives us then our formula for reversing the process for a to the x. Ish. Ha! Just kidding. No, it really does do it. There's no asterisk, there's no footnote, nothing. That's the formula. We are good. I say that with the knowledge that, right, e is still a special value because that natural log of a, even divided by 1 over natural log of a, if the base is e, that's still 1. I just get e to the x, right? But again, it's still the same formula. It just turns out to look better because that 1 over natural log of a all cancels and goes away. All right. Now what about the log function? All right, so this is the other sort of our remaining, for this video at least, the goal for the parent functions is to be like, okay, we've done the monomials, which are our polynomial terms, as well as our radical terms. We've done the exponential. What about log? So log, we wanted to have some function such, again, that we take the derivative and we get log. But already this should be sort of, there should be a warning light in your head at this point because there's something different about log going forward, meaning like taking that derivative, stepping forward. The derivative of log doesn't have a log anymore, right? I mean, it has the natural log of b, but that's just a constant. It doesn't have some sort of natural log of b or, natural log of x or log base b of x afterward. It all sort of goes away and becomes that 1 over x times some constant. So when you're taking a derivative of a log function, you're actually getting a totally different kind of function, which means we can't reverse engineer that process because we can't start with a log on the other side and sort of try to get backward. And in fact, it's even worse than that. In actuality, finding a thing whose derivative is log needs actually surprisingly advanced techniques. So this is something covered usually in the next calculus class, depending. So importantly, covered in techniques that are sort of outside the scope of what we're doing right now. And in fact, this is sort of a good hint moving forward that, like, this is arguably the first time in your sort of math process, your math career, where there are problems that you could relatively easily state, right? You could say, like, okay, what is, like, the result of reversing the process on log base b of x, right? What is the antiderivative or an antiderivative of log base b of x that nobody could actually solve? And when I mean nobody, I mean nobody. Not just like not the people in your class and not just like not undergrads or something. There are easily stated questions that mathematicians have proved don't have answers. So as an example, it's been proven that there's no actual sort of normal function as you might think of it, right? There's no sort of way of writing down an expression that is composed of all functions that you have seen before, such that when you take the derivative of that thing, you get e to the x squared. And it's not like e to the x squared is like this crazy exotic function, right? Like, it's not like I've like masterminded some crazy like sum difference and like put in division and all kinds of other things. This is a really relatively nice looking function, e to the x squared. Even when you especially when you think of the fact that e to the x is this nothing happens function in calculus, yet e to the x squared has suddenly broken everything, right? So this is one of those things where this is sort of useful to think about or keep in mind, especially if you're doing practice, that it really isn't a matter of like, I'll just write down a random function and then see if I can find an antiderivative of it. It's really easy to write down a random function and just end up with a real beast of a problem that you can't solve, and possibly nobody can solve. So keep that in mind as you go forward. It really is worth sort of making sure to use practice materials and stuff provided, because it's really hard to make your own at this point. Okay, so with that diatribe aside, what did we do? So we reversed the derivative process for, in particular, monomial type forms and exponentials. So in particular, we sort of developed the following. We know if we have x to the n for some, n that isn't -1, but could be any other real number. So 1/2 pi -17, right? Including negatives, just not -1 specifically because of this weird form we get. So as long as it's not -1, then we have this nice antiderivative sort of form, or what would be referred to as the class of antiderivatives, which again, this has to do with that plus c, and we'll get into that more in a separate piece. But is this sort of nice version. And this is commonly called an antiderivative, or sort of lazily the antiderivative when it has the plus c, although to be clear, technically this is an abuse of vocabulary because the antiderivative itself is a specific value. So you'd actually need like +7, not plus c. So when it has the plus c, it's what is the technical term is that it is the class of antiderivatives. There's another way of referring to this that we'll talk about later. Okay, I realize I'm going on a diatribe about the plus c, which applies to all of them, but again, this is a new piece in this video, and it's one of the ones that sort of confuse people a lot, so I'm trying to reinforce this idea. So I feel like I'm beating a dead horse, I'm sorry, but it is important. All right, so that left the n equals -1 case, right? We have the case where n is not -1, but could be literally anything else. So when n is -1 in particular, then we have this other form, right? This natural log of the absolute value of x plus c, where, again, that absolute value is absolutely important because the x could be negative if all you know is that you're sort of getting an antiderivative of 1 over x. In practice, so if you see this in sort of word problems, or if you run into this in the real world, you often run into a case where that absolute value is dropped, but that has to do with some background information that's telling you that x has to be a positive value. So unless you have that, you definitely need the absolute value. All right. And sort of last but not least, we have this reversal of the exponential version, right? So as long as a is some positive value, then we can get an antiderivative, or the class of antiderivatives, by having that 1 over natural log of a times a to the x, so that, right, we were trying to offset just like that 1 over n plus 1 bit. And again, that plus c makes its appearance. And that tells, then if we take the derivative, we get right back to the a to the x form, right? And as a special case in that previous rule, when a is e, right, when the base is e, then we really are trying to reverse the process of this e to the x, but remember, e to the x doesn't do anything when it takes the derivative, right? That's that thing where taking the derivative is itself, but that means the antiderivative is itself-ish, right? So we still need that plus c because it could have had some constant attached to it, but otherwise it's just the same thing. The other thing that we sort of ran into as a byproduct that's worth keeping in mind is that there are elementary functions, like normal functions we run into, like log, whose antiderivative actually turns out to be pretty difficult to determine directly. So there are sort of other techniques that we need to tackle these things, in many cases outside of the scope of what we're going to be doing. Okay? So that is that.